Good afternoon. Welcome to today's webinar on Thermoelectric Cooler. This is Hakam Al-Asawi, Technical Support Engineer at Al-Nadi Engineering and Agencies. We are the sole distributor of COMSOL Multiphysics in the Arab countries. So to begin with, we're going to talk about the Thermoelectric Cooler, or TEC to be short. Thermoelectric cooler is a device made out of a PN junction semiconductor. When you apply a potential difference across the junctions, it's able to pump energy from one side to another. So you're cooling one side and you're pumping the heat to the other side. So it can be used as a cooling device in a replacement to compressors and with the expansion fluid, like for example, refrigerators and so on, in very tight spaces. Although the efficiency is not as other reciprocating devices, but it can be formed to different shapes, used in micro sizes, very small sizes, you can see. And it can adapt to a different, very specific applications, which does not look into the efficiency of the cooler itself. So the model would look like as follows. Basically, the thermoelectric cooler is made out of very small piles of the semiconductor. Each pile or each column of these is made out of a P junction or an N junction of this semiconductor. There's certain specifications for this semiconductor. It has to be conductive to a certain extent to eliminate the unnecessary heat generation due to resistance. And also it has to be more or less non-thermally conductive to a certain extent to not be able to transfer the heat generated on one side to the other and ruin the whole cooling effect of this device. And other properties can be used, can be necessary for these operations. The whole idea that we have multiple piles connected in series where a potential difference is applied across the whole system, and thus the system is operational. In our case, we're just going to model two piles at P and N junction, where potential difference is applied from one side, and the other side is grounded to the earth or to close the circuit. And these two thick layers, are ceramic material, some sort of maybe alumina. We're going to select an alumina in our case, some sort of ceramic material. One of them is going to be hot, and the other side is going to be cold. So to begin with, we're going to start using our COMSOL. So let's switch to COMSOL. When we first use COMSOL, when we first use COMSOL, we're just going to open the new page. So we're going to select Model Wizard, and this is our model. It's a three-dimensional model, so 3D. And under 3D, I'm going to go to Heat Transfer, scroll down. I'm going to find the Thermoelectric Effect Multiphysics, which is a prepackaged features all in one node. If I click Add, it's going automatically to add the heat transfer in solids, electrical currents, and the multiphysics, combining them to create this multiphysics feature. I can click on Study, select my station to study, and click Done. I'm going to define some parameters. So the first parameter is the applied current. Let's call it I naught. And in our case, we're going to start with 1 ampere. So 1 ampere, like that. The description is going to be applied current. This current we're going to apply to the terminal feature under electrical current later. This is the first thing. Next, we're going to start with our geometry. Our geometry is going to be in millimeter. And under geometry, I can start by building my geometry that was in the slides. So let's go to block to establish our base. My block dimension is going to be 3 millimeter. by 1.5 and 0.3. So this is my first block or my base plate. And then I can start building my final geometry over it. So I'm going to use one way to create that. I'm going to use the work plane. My work plane is going to be above this base plate by around 3 millimeters, 0.3 millimeters, like that. So it's just going to be above it. I can go into my geometry now. I can draw my other rectangles. And these are going to be my terminals. So it's 1 by 1.2. And the location is going, the coordinates is going to be 0.3 and 0.15. So this is my first one. I need another one, but I need to just be pushing it in the right hand direction. So I can just duplicate this one and change the coordinates to 1.7 in the x direction, like that. So these are my two electrodes or my two terminals. After I finish it on my work plane, so it's gonna look like this. I can extrude it to the desired height, which in my case is just 0.1 millimeters, like that. So these are my two terminals. One of them is going to be ground. Next, I can create another work plane to draw my two piles. So in this case, the z coordinate is going to be the 0.1 from this thickness of the second plate plus 0.3 from the thickness of the first plate. So as you can see, it's just on the top of the terminals. My pile dimensions are going to be just two other rectangles, a little bit smaller than the base plates or the terminals. So it's going to be 0.1, 0.9, and 1.1 by 0.35 and 0.24 coordinates or composition for it. So this is my first one, and then duplicate it again and push it to the right hand side in the x direction. 1.75, like that. Extrude this one again. You can go to my work plane, extrude it. And the height of these two piles is going to be 1.5 millimeter. And then I can duplicate the first work plane again, or if I'm going to connect this in series or something, I can create these in series, so I can just create a new work plane instead of duplicating any work plane. So create another work plane. This case is going to be, we said 1.1 plus 0. What was this again? 0.1 and 0.3. And the extrude for this one is 1.5. So this work plane is going to be 0.1 plus 0.3 plus 1.5 to be on the top of this part, yeah, like that. And then I can draw my jumper or my plate that's going to connect these two pieces together. It's just going to be a rectangle with the following dimensions: 2.4, 1.2, and the coordinates is going to be 0.3 and 0.15. So this is what's going to look like after I extrude it for 0.1 as the first terminals, like that. So this is almost done. I need another block on the top, so I can just duplicate the first block and just change the coordinates of the z direction of the z coordinates of this block to 2 millimeters. And now it's all on the top here. So this is the geometry and it's done. Next, I can move to my material, and this is a very important part because this is how I'm going to define a P junction and an N junction. I can go to my materials, add from library. I can start by the basic materials, which is copper for the conductors, alumina for the two ceramic plates on the top and then the bottom. So the first one I selected is assigned for all the domains. So I'm just gonna leave it as is. When I select alumina, I'm going to select the top and the bottom plates, and by default is going to be omitted from these copper domains. And another material, which is the semiconductor, I can go to the thermoelectric library part, bismuth telluride. I'm going to create two nodes out of this bismuth. One of them I'm going to define as the P junction and the other as the N junction. So for the P junction, you're just going to type P at the end, dash P. And leave it as is. The other one, I'm just going to define it as N. And in the N, I'm just going to add a negative sign at the Seebeck coefficient. So yeah, that's it. For the P junction, I'm going to select this one. And for the N junction, I'm going to select the other one. Just make note of which one is the P junction and which one is the N junction, because it will differ where you apply your current and your ground. Next, going to the heat transfer in solids. I will apply a temperature domain, a temperature boundary condition, which will maintain the temperature of this side at a constant room temperature. Or I can apply heat flux boundary. That's one way also to see how much energy is dissipated, or assume how much energy is being dissipated from this side. There's many ways to define it. This is one way to define it. Next, I can go to the electrical current node, select one of the boundaries as a ground, and select my ground to be, let me just do the transparency. Yeah, this one. And this is my ground. And apply a terminal boundary for the other side of this semiconductor. So I have the ground and I have the terminal. For the terminal, I'm going to use current, and I am going to use I note. The I note is from the parameters, so it's going to be grabbed later. Going back to the electrical current, I will just skip or unselect the ceramic plates because there is no calculations or there is no simulation. I do not want to include in the equations for the electrical current. And for the heat transfer, I'm going to make sure that it's selected for everything. You can use the automatic mesh for now. It would not do that much difference since this is a very simple model. If you have a bigger array of these semiconductors and piles, using a manual mesh or an optimized mesh would make a big difference in the calculation. The last thing, I go to my study and then click compute. It shouldn't take that much time. If you have any questions, please use the chat or use the raise hand function and we can answer your question. So there's undefined material property for which one? For the copper. Let me check. Yes, this is the error here. We would like to remove the cover from the thermoelectric effect. So unselect it from this, and it should work now. So we had a question how to get COMSOL. You can contact our sales team. I can send you my the email of our sales team, which is I'm going to send it in the chat box here. So this is the email of our sales team, and you can contact them, and they can going to check what kind of features or modules you would like in your suite, and they're going to provide you with the service. So the model is done now. We can see how it works. As you can see, this is the temperature difference between one side to the other. So the hot side is the white one, and the cold side is the red one. I can change the colors for the legend. If I go to the plot here, instead of thermal light, I can use the spectrum or rainbow. So rainbow, hot is red, cold is blue. And we can use a different kind of study. We can add a parametric solver. So parametric sweep for the current. I can have my current start at 1 amp and going up to 9 amp for the step of 1 amp. And we can see how changing the current would change the maximum temperatures and minimum temperature of these surfaces. So now the model is going to be run 9 times from 1 ampere to 9 ampere with a step of 1 ampere, and you can see the different plots for all these different current values. You can also have there's an automatic plot for the electrical potential. You can see also the potential, the voltage used between each plot. You can have different tools. So for example, you can use the probe tools and surface integration to see the maximum delta temperature between two surfaces. So how much current you apply and what is the delta T between the two surfaces. In the meantime, if anybody has a question, please you can either use the raise hand function or ask in the chat box. It's going to take a little bit more time this time because we're running basically the model 9 times. Last time it took 31 seconds. It should take a little bit more this time. So if you're asking how to get to be more proficient in using COMSOL, there are multiple ways. Either attend a training course on COMSOL Multiphysics or go to the website. There is a lot of video tutorials and blog posts guiding you how to create different types of models and explaining the different features. There is also the user manual, which is included in the software. You can see all the different features and how do they interact with each other in the user manual. It covers every aspect of the software. And if you face any problems, you can always ask COMSOL support, and they will help you and guide you through it. Okay, so 2 minutes and 9 seconds. So at 1 amp, these are the values: 2 amps, 3 amps, 4 amps, 5 amps, Okay, I think there's something being really distorted here because we're using the temperature, we're fixing the temperature of this phase. So as we increase the current, the temperatures just go haywire. So if we use a heat flux boundary instead of temperature, I think it should work better. So we can disable this and use a heat flux boundary on this surface. Use a convection heat flux, external natural convection for a solid, and it's a horizontal plate like this. And we can use this length area or perimeter. We can use these features to calculate it again and create a more